if it's really a high temperature superconductor, you would expect to see numerous replications which all agree, and they would show the measurements that you described, show it going through the transition and so on. So at the moment we're a long way from that. All we've got is this some indications of low resistivity, although the data don't look terribly good, and this rather, what I described as rather lethargic. Now, given the size of that magnet, I would expect that to
propelled up to the ceiling.
Absolutely, yeah.
What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist, here again. I hope you've had an amazing week and have a brilliant weekend in store. Now, this week, the science news has been dominated by the idea that the modified lead apatite structure LK-99 could be a room temperature and pressure superconductor. Room temperature and pressure superconductors are one of the holy grails of science. Such a material would display zero electrical resistivity and would help to reduce transmission line losses, prompting massive energy and carbon savings. Such materials would also be invaluable when constructing fusion reactors or future particle colliders, and may even help us make progress in the fields of quantum computers and superfast transport. Some have even speculated, without evidence mind you, that such a material could open up the worlds of anti-gravity and explain the seemingly physics-defying manoeuvres of UFOs or UAP. Room temperature and pressure superconductors are a massive deal. But do we have one on our hands with LK-99? To help me dig into where we currently stand with LK-99 and how we're going to get confirmation of whether it is or is not a room temperature and pressure superconductor, I'm joined by a phenomenal special guest, Professor Simon Clarke. Professor Clarke is a professor of chemistry and a tutorial fellow at Exeter College, Oxford University. His undergraduate and graduate research was carried out in Oxford on aspects of solid-state chemistry and magnetism. He gained a Royal Society NATO postdoctoral fellowship to work on nitride chemistry at Cornell University and then returned to Oxford. He has received numerous scholarships and awards and was the head of the inorganic chemistry section of the Oxford Chemistry Department from 2019 to 2022. So who better to help me understand the hype around LK-99? So, Professor Clarke, we've heard a lot of hype around the potential room temperature and pressure superconductor LK-99 this week. Could you give us a very brief overview of what a superconductor is and why a room temperature and pressure superconductor would be such a massive deal for the world and why people are so excited about this?
Okay, well, you've got a nice picture there of a conductor.
Try to be helpful.
Levitating above some magnets. I guess people are familiar with the idea of metallic compounds that conduct electricity.
Yeah.
And when you pass a current through a metal, then there is some electrical resistance. And the difference between a metal and a superconductor is that a superconductor conducts with no electrical resistance. So a lot of metals, when you cool them down, become superconducting. They enter this superconducting state, which is a sort of fundamentally different state to the conventional metallic state. In a superconductor, pairs of electrons essentially couple together, and that means that the electrons behave in a completely different way to the way they behave in a normal metal. I sometimes think of an analogy where if you've got you might have two teenagers in different parts of the country, behaving independently. So that would be the normal metallic state where they're not strongly interacting. If one telephones the other, they become strongly correlated. And that's a bit more like the pair. That's sort of my analogy of the pair that forms in a superconductor. So superconductor has this property of zero electrical resistance because the electrons are forming this so-called Cooper pair. And they behave as bosons rather than fermions. The other property that a superconductor has is that it completely expels magnetic flux. So if you have a compound in the superconducting state and you bring a permanent magnet towards it, it will be repelled by the magnetic field. So that strong diamagnetism, repulsion of a magnetic field, is the other hallmark of a superconductor, and it's a very strong diamagnetism. So we should probably just say that a lot of compounds most compounds are diamagnetic. It's a property of any sort of pair of electrons in an atom that they have a small diamagnetism. They weakly repel a magnetic field. But in a superconductor, you've got this very much stronger diamagnetism.
I think you said it's a perfect diamagnetism. You can think of it some ways.
In fact, yeah. So it perfectly expels the magnetic flux. So there's you can imagine lots of applications for superconductors. The main application for superconductors, or one of the main applications, is in making electromagnets, because if you have this supercurrent, this current that's persisting with zero resistance, you generate a magnetic field as a result of that, and so you can use that in an MRI scanner, or some other magnet. And a superconductor tends to be able to carry quite a large current. The larger the current, the stronger the magnetic field you can generate. And all you have to do to generate that high magnetic field is keep the superconductor in its superconducting state, which has a relatively low cooling load associated with it.
This was something that we that I see for particle colliders going forward, particularly particle colliders that have decay products spray against the wall. So, for example, people have talked about a potential muon collider where the muons are decaying and hitting the wall. That puts heat into the superconductor, and the worry, therefore, is that they can quench, and then they stop the particles going around. But if you could produce something that has a very high quench point, close to room temperature or even higher, then obviously those thermal loads become not so much of a problem. So people have talked about applications potentially for fusion reactors, potentially for future particle colliders, things like this. So it's very exciting.
If you want to make a fusion reactor that produces net energy, then you need to use a superconducting magnet to confine the plasma. If you try to use a conventional electromagnet, the cooling load that you would have to apply would be more than you would generate in the fusion reaction. So there's also a general correlation between the size of the current, the maximum current that a superconductor can carry, and the maximum magnetic field that it can withstand before it goes into the normal metallic state. Those generally correlate with the temperature, the superconducting transition temperature, the TC. So that's one of the reasons why a higher TC superconductor would be useful, because it would allow you, even if you operated it at low temperatures, it would allow you to carry generally speaking, a larger current.
Very interesting.
Than lower temperature superconductors. It would also, if you could maintain the superconductivity at room temperature, that would obviously usher in a range of other devices.
People have talked about things like low loss transmission lines and things like this. Obviously,
that's right. Yeah.
When we're passing currents around transmission lines, to some extent they heat up, which is limited by having high voltage, but to some extent they heat up. That's energy loss. That's potential carbon savings, energy savings we could have if we can reduce that resistivity of the material we use in the lines.
That's right. Yes, I'm not an expert in that field because I'm a chemist making new materials, but certainly there will be a range of applications in the power industry, and I think there's already a copper oxide superconductor demonstrator in New York transmitting power.
I'll have to have a
look at that has to be cooled to low temperatures.
Amazing stuff. So some very, very interesting potential applications. So one thing we're told is that LK-99 has been described as a modified lead apatite structure, which is far beyond my understanding of the material science. But could you give us a quick idea of what that means? And is this a particularly exotic material, or is it something that we might expect to see superconducting properties in, or is it something that's completely new, or something that's just completely old hat?
Okay, so apatite is a mineral. So the apatite mineral is a calcium phosphate, and that has calcium 2+ ions and phosphate tetrahedra. You can see those in blue there. These compounds are this structure can accommodate other ions. So, for example, in this case, all the calcium 2+ ions in the original mineral apatite have been replaced by lead. So you can make lead apatite. And there are some additional, as well as the phosphate groups that are in the blue tetrahedra on your diagram. There's also accommodated in the case of the lead apatite that we're talking about, there's an oxide ion accommodated in that sort of channel that you can see in the middle, surrounded by the lead ions. So it's a not a particularly unusual type of crystal structure for a mineral. Of course, in the lab, we can choose which elements to incorporate. When people ask me what I do, I sometimes say that I sort of make synthetic minerals, because we can take whatever elements we want to in whatever ratio, and we can try and often make compounds with crystal structures that you find in minerals, but with different elements and therefore different properties.
Yeah.
So the lead apatite would be one of these diamagnetic insulating compounds, and what's been done apparently in LK-99 is that people have tried to replace some of the lead ions by copper ions, about 10% of them. I have to say that it's not been proven exactly what they've made in this case. There's very little characterization of the crystal structure. No real. It's clear that there's a compound with the apatite structure, but the synthesis that's been described is such that it's a slightly unusual synthesis. If you wanted to make the compound that
is claimed.
Yeah. So it's guaranteed to have quite a lot of stuff left over, quite a lot of copper sulfide, and you can see that in the X-ray diffraction pattern that accompanied some of those papers.
Does that make the replication efforts more difficult, and also make it hard to work out if there's some sort of combination effect going on rather than?
So what I don't know is whether sometimes you could imagine there might be electronic effects associated with two different crystallographic phases being in contact. I don't know whether that's what's happening whether that's relevant in this case.
But the higher level idea is that you need to know exactly what you've got to be able to understand what you've got.
You certainly need to make, in my view, pure material where you know the composition, you know the crystal structure, and then you can measure the properties. So measuring electrical resistance in a multi-phase sample, you don't really know what you're measuring. So that's a big challenge. Any measurement where you have to attach electrodes to your sample relies on you
knowing what's between those two electrodes for a start.
Yes. So I mean, that's one of my concerns about this field, that there doesn't seem to have been any attempt that I can see yet to try and make single phase copper substituted lead apatite.
Okay.
And so it's that's still to be investigated. I mean, if you were to take lead apatite and substitute some of the lead ions by copper ions at the 10% level, one would normally expect that compound to be an insulator, and you would expect it to be paramagnetic, because the copper ion, if it's a copper 2+ ion, would would have one unpaired electron, and that would mean that the compound would be attracted weakly to a magnetic field. So it would behave as a paramagnet. So I would be surprised if that compound was
exactly as described, perhaps.
Yeah, I would. That's right. So if it was really that composition, I would be surprised if it was conducting, let alone superconducting. The fact is, it's present in a composite. I don't think it's been proven that any copper has been incorporated on the lead site, because no one's done that analysis as far as I can see. And there are other phases present in the sample. So overall, it would be surprising. Now, it's true to say that the history of superconductors shows that they sometimes appear when you're least expecting them. So the copper oxide superconductors, which were discovered in 1986, they were discovered when an magnetic insulating compound was the composition was changed to change slightly the electron count in the material, and that turned the compound into a metal. And at low temperatures, it was discovered to be superconducting. So a general rule might be for discovering superconductors is you might want to introduce some mixed valence of any transition metal ions that you've got, move away from a simple stoichiometry, and then sometimes unusual effects appear. There was so
it's not disqualifying that experts might not expect this to be superconducting. It still could be. It's not 100% disqualifying, but it would be surprising. In the apatite case, I think it would be very surprising. There are partly because the amount of the transition metal copper is rather small. In the copper oxide superconductors, they're much richer in copper, and the coppers are in fairly close proximity. There was another class of superconductor discovered about 15 years ago, which were based on iron arsenide layers, and they also were not the sort of place you would have gone looking, I think, for superconductivity. There was a group in Tokyo was doing sensible things to some solids, and they unexpectedly discovered that they could make a series of superconductors, and that field lit up in 2008, 2009. We were part of that sort of frenzy of making new iron arsenide and iron selenide superconductors, and that was a very exciting time. I think it's a very different feel this time, because at the moment in this case, there's no clear evidence that there's actually no clear evidence for a superconductor, I would say. I guess that's something we might that's actually kind of a really nice segue into what I wanted to say next. So we've seen an awful lot of hype, that this is potentially a room temperature and pressure superconductor. So as an expert, have you seen anything that points strongly in that direction? Are there a lot of positive signs, or are there just too many red flags? How do you weigh the evidence? I can point to a couple of those things as well to kind of tick off.
Right. I think there are these videos of what I would describe as very lethargic levitation.
I can probably bring one of those up.
You might have that. I think it was on your sort of title.
Yes, it was. I just got to find out. Yep, I've got it in here somewhere.
So that, I have to say, that's a very big magnet and a very small piece of the material.
Probably a neodymium magnet or something like that.
Yeah, so it'd be a neodymium iron boride magnet, very strong permanent magnet, and there's clearly some repulsion of the sample by the magnetic field. It looks a bit like a superconductor might behave.
In this groundbreaking,
but there are compounds like pyrolytic graphite, which have a rather strong diamagnetism and would be repelled by a strong magnet.
So just to kind of draw a line under that, a lot of people are doing these replication attempts. It's been a buzz phrase, make the rocks float. But that's not enough, is it? Because this could be a diamagnetic effect. It's not necessarily the Meissner effect. It's not necessarily superconducting. So 10, 15, 20 people in their garage making some little specks of stuff float around is not necessarily, well, it's definitely not going to prove that this is superconducting, even though it might be interesting and weak evidence in that direction.
So the way, so one thing I did want to say actually is these lead compounds would be quite toxic. So there's a little bit of me that's worried about people trying to replicate in their garage and not taking sufficient precautions. Avoid eating it, avoid inhaling any lead vapors, and wear safety spectacles. So in fact, I would discourage anyone from working on this outside a sort of managed laboratory facility.
So I actually hadn't thought about that, and I thought the kind of the guy doing his garage was quite interesting. But having thought more about that and having had you comment on that, perhaps it's not as potentially wise. I don't know what his expertise are, so maybe that mitigates it to some extent. But yes, that is very much a concern that people should be aware of.
I think that's right. Health and safety these days, I mean, I think it is taken a lot more seriously and rightly so. And lead compounds, as we know, are very toxic.
Yeah. In terms of the scientists involved, I've heard that they're very credible scientists. It's not my field, so I can't speak to that. They claim to have seen these drops in resistivity that they've presented in their symposia and in their slide packs. Anything interesting there, particularly twinned with these claims coming from Southwestern University, I believe, where they've said they've seen superconductivity in this material after their synthesis, when I can get the word out, below about 110 Kelvin. Is there anything that we should read into that, or is it again a little bit too early to say anything?
Those, I have to say, those data don't look terribly
okay.
The data don't look terribly good, I would say.
They get thrown around Twitter, obviously, without much kind of peer review or experts.
Yeah, I would like to sort of see cleaner data in a way. I'd also like when the measurement really should be done on a pure material. If you're going to, if it unless it's some sort of strange interface effect, then which would be very sample dependent probably. Then I'd like to see measurements on a pure, well characterized material, particularly of the resistance.
So it's kind of, even if you're getting these nice things, the bottom line is you still don't know exactly what you have. So how useful is this? I
think certainly with my as a chemist, I'm.
The point you're making is getting through to me loud and clear, is what I'm trying to say.
Interested in the purity of the sample and knowing what it is, and if it, I don't know, if there is some strange effect because of it being a composite, it's equally important to know what that is. What is the interface? So I'm not yet persuaded that there's really a superconducting phase, but there evidently is something fairly diamagnetic. So I think it's there will no doubt be further publications on this stuff.
It's probably worth flagging up at the moment, just for people watching as well, that there have been a few replication attempts. There have been a couple of people who've claimed to see superconductivity below a particular temperature, or they've managed to make the rocks float, quote unquote. But there's also been a couple of experimental efforts by teams at the National Physical Laboratory in India, in New Delhi, and at Beihang University in Beijing, where they say they've synthesized LK-99, but they've seen no signs of superconductivity.
That's right.
There's a third experiment, this one at Southeast University in Nanjing that we were talking about, where they found no Meissner effect, so this levitation, but they had near zero resistance below 110 Kelvin, which is still very cold, far from room temperature, but an interesting effect. So there's seems to be very much a mixed bag in these replication efforts, even from experts who are kind of looking into this. So it's unclear what's going on at the moment, and people should be obviously excited, cautiously optimistic, but not going over the top on this at the moment.
I think the variability is a concern.
Definitely.
I mean, as a solid state chemist, one sort of dreams of making a room temperature superconductor, and you would hold it in your hand and levitate a magnet, and you would expect it to be, perfect diamagnet, and you would also expect other labs in the world, any other lab in the world, to be able to follow your synthesis and obtain exactly the same results. And with the copper oxides and the iron arsenides, that was generally true. If people were successful in reproducing the phase, then it was superconducting as originally billed. So that's another. There are credible people who've tried to make it. They've used the same method, so they've still got this composite material, as far as I can tell. But there's no the pieces were resolutely stationary on the magnet.
And you pointed out this. Where is it? I'll just go find it. You pointed out this nice piece on the archive where some people have kind of gone more into this. Some remarks on the possible superconductivity of composition. Of LK-99, which might be something that people want to look at as well.
I think that appeared this morning, and they make it clear that there's this, that it's not a single phase material, and so I think that sort of, that was a fairly sober. It doesn't get us, in a way, it doesn't get us closer to the answer, but it was a sort of fairly sober comment on all this. So
no one should be going and stealing the lead off church roofs and
definitely not. No, definitely not. No. Because definitely not, because I think the superconductivity is not proven, and it's illegal.
That's another reason as well.
Yeah, I think that's important. There have been several papers doing computational work on the published composition, the supposed composition. But of course, if you want to do computation, you have to know that composition is accurate.
We've seen this one, like the origin of correlated isolated flat bands in this potential material.
That's right. I think all the computations agree, but they have to rely on the composition being accurate. I would say I think it's, from the computation, it's difficult to explain the superconductivity from the computations that have been done. So it's not. I mean, it's a natural thing to do the computations, but I don't think the results of those computations are surprising. They're sort of they're the band structures that you get are what you would expect for a rather dilute set of copper ions in a salt. You would have these very narrow bands, almost isolated levels at the Fermi level, which just corresponds to copper being in the +2 oxidation state.
So this computational work and the results that come out of it would probably be, would it be fair to say it's a necessary but very far from a sufficient, condition for having this superconductivity?
They can't. Yes, they don't show that there should be or shouldn't be superconductivity. I still find it would be surprising if there were superconductivity in this composition. I think most solid state chemists would say that based
which would be exciting in itself, but still we should be cautious beforehand.
Yeah, indeed.
So that very naturally leads us on to, I guess, what is the most important question in all of this, which is, how can we get confirmation? What tests would LK-99 need to pass to be proven to be a room temperature and pressure superconductor and not just a non-perfect diamagnet? What tests would experts be looking to perform to prove this once and for all?
Yeah, the main test I would do would be to measure the diamagnetism and show it passing through the phase transition, passing through the superconducting transition. So in the original paper, there is a measurement of the magnetic susceptibility. And conventionally, to test a superconductor, you would cool the sample through the superconducting transition in the absence of a magnetic field, cool it into the superconducting state. You would turn on the magnetic field and you would measure how magnetic it was, and it should be a perfect diamagnet. So it perfectly repel the...
So basically, to make this kind of simpler for people, we see these beautiful Meissner effects where something is floating around on a track, but really that should be temperature dependent. It should not do it above a particular temperature, and then it should kind of do it below a certain temperature. The
superconducting transition temperature, the TC, is the temperature below which the sample is superconducting. Above that, it's a normal metal. So it wouldn't be diamagnetic or wouldn't have that strong diamagnetism. So that's part of the test. You would turn on the field at low temperatures, and you would measure the magnetic susceptibility, how magnetic it is. You would get to the transition temperature, and the diamagnetism at that point will have reached, will have gone away. And you would in most superconductors you would have a weakly paramagnetic sample with a temperature independent paramagnetism. That's characteristic of metals. The next thing you would do is leave the field switched on, and you would cool the sample again through the transition temperature back to low temperatures. And what will happen then is that in the normal state, when you've got the magnetic field applied, the magnetic flux will penetrate the material. And when you cool through the superconducting transition for most superconductors, there will be incomplete repulsion of the...
I think we should be able to get a nice potential image for this. If we've got put Meissner effect, it's usually got the kind of these images that we want to maybe that you're talking. I think this is kind of the idea that you're talking about.
So that's right. So the flux penetration above the transition, expulsion below. But in most superconductors, there will be, when you cool in the field, there will be partial penetration of the of magnetic flux into the sample that is preserved. So you get some trapped magnetic flux, and the sample is not quite as diamagnetic as when you turn the field on at the lowest temperature, when it was in the fully superconducting state. So that's the test, the difference between that behavior where you cool in zero field and then you cool in a field. Right? You have slightly different responses. Now, in the original paper, they do show something that looks a bit like that. But they don't go through the transition. They never get to the point where it doesn't seem to be superconducting anymore.
So it's sort of tantalizing, but not enough.
Coincidentally, it seems to be the temperature that's the maximum for their measurement, the maximum temperature they could reach. Turns out to be the TC. So I would like them, they should measure well above that temperature. If you know these levitating samples, if you heat them up to well above this proposed superconducting transition temperature of about 120 degrees C, do they stop levitating at that point? Would be sort of partial test. So you have to go through the transition and show that it goes from being a metal to becoming a superconductor on cooling, and there should be a heat capacity change at that transition. So measuring the heat capacity would be a standard test for a superconductor. And the other test you can do, although I mentioned the drawbacks, technical difficulties, is to measure the resistance, which should drop to zero quite suddenly at the transition temperature, and that that just requires skill to measure it accurately. The magnetic test is easier because you don't have to attach anything to your sample.
Should we be expecting naively? We're seeing these videos of things, kind of limply kind of floating above a magnet. Should we not be expecting to see, these kind of things racing around tracks and being kind of flux locked to tracks and These
That's
kind of
right.
things
So,
that you can see with a superconductor.
yes, indeed. So on that diagram, they will have they've cooled the they've cooled the material into the superconducting state while it's being exposed to the magnetic flux of the magnets on that track, and so it, as I mentioned, that flux penetrates the superconductor slightly, so it gets locked in to the magnetic field of the track. So you should be able to do that if you were to take this new material, heat it above the superconducting transition, cool it down on that track, and then you should get it to race around the track, but without the need for cooling it. They've got some sort of onboard cooling on the piece of superconductor in green there.
I heard some comments about from Professor Fura when I was looking as well, that the Josephson effect, which very, very far back in my history as a physicist, I kind of remember the name, but I don't remember exactly what it was. But he was saying that this thing could potentially show the Josephson tunneling or AC Josephson effect. Is that something you might want to look at?
That's what you would expect to find in superconductors. So you should be able to see that. You should be able to see that effect. So you should be able to see all the effects that.
What is that effect? Sorry, because I'm just kind of I can't remember exactly what that was.
Yeah, so it's as shown there. You've got you insert an insulating barrier, and it is possible for the superconductivity to persist.
It's just quantum tunneling, but it's quantum tunneling
barrier.
Basically. Right?
Yeah,
okay.
Essentially. So people would carry out those sorts of measurements. That's probably maybe not the first thing you do.
Yeah. But I guess the point that you're sort of the higher level point that you're sort of getting at here that we haven't really said yet is that you would expect to see 2, 3, 4 of these telltale signs reproduced by multiple groups before we can be confident that we're seeing a superconductor, and that's not the stage that we're at as yet.
That's right. I mean, I think if this was a clear case of a new superconductor, we would already have seen reprints showing the Meissner effect, the heat capacity transition, and zero resistance from a number of reputable groups in China, USA, all around the world, Japan, and so we haven't got that. We've just got these sort of glimpses of something diamagnetic. Which is a little bit unsatisfactory, to say the least. And there's this uncertainty. For a chemist, there's this uncertainty about what is the composition. As far as I can see, there hasn't been any microscopy of any type carried out on these materials. Especially if it's a composite, that would be something to investigate. How does the composition change across that piece that's shown there on top of those magnets? What is it? Is it apatite embedded in copper sulfide or something like that, or other phases present?
Which could be interesting in itself, right? If there's different interesting phases in there, or interactions between phases that are doing strange things, could be, I guess, interesting of itself, naively to someone who's not expert in the field.
No, I think that's right. Yes. I think it would need to, but it needs to be investigated in a lot more detail.
So I guess the bottom line there is there's lots of work to be done if this is to kind of pass those bars. All that stuff would have to be published, which obviously takes time. So if you're still interested in this thing, you really think it's going to be, going to hold up, that's going to take time, and you're going to have patience before we can meet those bars and people in the field can be convinced.
It's going to take some time. It always takes a little bit of time to do things. Do things fully and properly, but it can move. These things can move at quite a pace, and I think the archive has enabled that.
Yes.
So, I think the thing with the archive, it's been stressed in most of the articles on this compound that it's not been peer reviewed, which is well, sort of true. If peer review is understood to be, you submit it to an editor of a journal, the editor looks at it. Says, yes, I'm going to send that out for review, sends it to 2 or 3 people, experts in the field and ask them to review the work and give comments back. So
but reputable people will still put stuff up on archive if they have it.
Well, that's absolutely right. So in fact, it's a more the archive. The stuff hasn't been peer reviewed. So, but you're putting it in this public repository.
Yeah.
So in fact, you're exposing yourself to peer review by everybody.
Yeah. And reputation. If you're just saying rubbish, there's a reputational.
Well, that's right. So we did submit. I don't use the archive very much. I have submitted things to the archive in the past. It's much more. You have to be much more sure of yourself than, if you like, or it's more stressful than submitting a paper to a journal.
Yeah, which is kind of behind closed doors. And
yes, that's right. So you think, well, what if we've made some honest mistake, and if you send it to a journal, the editor sees it, the reviewer sees it, and they say,
you made a daft mistake. Right, go away. It's fine. Whatever. Yeah.
So, but on the archive, it's there, and you can't get rid of it either.
Yeah.
The previous versions are there. So it's a sort of, in a way, it's a more testing forum. So that's.
I remember in my field, you might have come across it sort of 10 years ago when I was doing particle physics. The faster than light neutrinos was a big thing in the field.
Yes, that's right.
And the scientists were just like, we don't think this is physically real, but we have looked and looked and looked and looked, and we cannot find anything wrong with our experimental setup. We have to publish. Please kind of look at this. And people kind of looked at it and they said, okay, you've messed up. This wire is loose. And eventually they worked it out. And I don't think there was particular reputational damage, because they said, look, this is interesting. I'm going to put it up. The community is going to look at it. But there was that huge amount of influx of people interested and kind of, working to try and work out what this was. So it was a very stringent test of that thing, even though it didn't, I can't remember whether it went forward to peer review or whether it kind of was worked out beforehand. But
I do remember that case. And I suppose in that case, it's an example where they, in effect, they were sort of asking for help.
So I wanted to switch on to, just as we kind of come towards the end of this, because I don't want to keep you too long on a Friday evening. I appreciate you taking the time. So I want to switch on to a little bit of the kind of social side, because there's been an awful lot of hype around this topic, as you'd expect with something that has such far-reaching applications. Nothing wrong at all with people being excited about this. But what have you made of the interest in this potential room temperature and pressure superconductor and the reporting and the kind of social media furore around it? Have you got any comments on that?
Yeah, I mean, I think it shows how how fast news travels and how people are sort of plugged into various forums.
Yeah,
and it, I think that's something that's obviously changed over, well, certainly since the previous sort of flurries of superconductor discoveries.
I guess the positive is that it's getting a lot of eyes on fundamental physics. It's getting a lot of eyes on superconduction specifically, which may be, I'm certainly not someone who begrudges that. I was working at the LHC when it turned on, and we were getting all of this interest and this kind of thing. So don't begrudge anyone that. But I guess the negative is there seems to be a real sense of chaos and maybe people kind of lose trust. A few people have said to me that, room temperature superconductor, the last one fell apart, and is this just not like cold fusion? And I was like, well, no, it isn't, because there are superconductors. But is there there's a kind of seesaw, isn't there, between getting engagement and not necessarily undermining trust in a kind of very interesting and valuable field.
Yeah, it is a bit chaotic. And I guess we'll see over, probably fairly soon how things are going to pan out.
It's going to be very dependent on whether it holds up or not as well, isn't it? Because if it holds up, all the complaining about the hype, I guess, goes away, which it shouldn't really. It shouldn't be so kind of results dependent, but I guess that's what's going to happen.
I suppose it should be. I suppose it should be. When the results are
Well, after the results are after we're sure. I mean,
then we'll be where we are,
yeah.
and it may just be that it's a just another modified appetite. The thing it seems to me is what one I suppose has to explain this unusually large diamagnetism that seems evident. But time will tell whether there's whether any part of that sample is superconducting.
If this doesn't hold up, do you think it will have any kind of bad impacts on the field or not? Because I've kind of been arguing this week that, like, look, be cautious. This is very exciting, but don't go crazy. And we've seen issues like the Rangadius problems and the retractions that we've seen. Don't jump on this, because the next set of scientists who come with very interesting structure, very interesting potential room temperature superconductor are going to have to go through all of this rigmarole, whereas the people who are kind of boosting it now will have kind of left and moved on and got their clicks and likes. Maybe I'm being unfair, maybe I'm seeing too much, but I just wondered how you think that kind of balance between hyping it to the moon immediately and far ahead of the evidence and the engagement, where that sort of pans out, and whether that could have any negative effects.
I think if the hype persists, probably if the hype persists for too long, then it could have a damaging effect. If there's really nothing there, so I think it's probably be good if things come to a head fairly soon. But I don't think it'll stop people
being interested in this area.
That's right, and doing discovery-led science on the fundamentals of superconductivity. Trying to understand, trying to understand how the current copper oxide superconductors work.
Maybe I'm just being a little bit of a stick in the mud then on that stuff.
Well,
it's quite possible.
One doesn't want to, I suppose, give the impression to the general audience that there's chaos, and I suppose it shouldn't be. I mean, the science shouldn't be a matter of sort of opinion, I suppose. I mean, inevitably people have opinions about whether they think this is real or not, but they should be. It should be provable one way or the other. So
I've seen some scientists kind of having fun with it. Here's a scientist who was saying, I've made a fork-shaped LK-99 sample, and he's just got a bit of tape above the thing, kind of saying, look, wait for the evidence. We're seeing all these grainy videos, but come on, let's be calm about this. So there is, I guess, slight irritation from experts in the field, but also they know people are going to be excited about this. They know people are going to jump on board, and there's, It is good to see people being excited about fundamental physics at the end of the day. I think
that's true. Yeah, because it is important. There'll be fundamental chemistry and physics. We'll discover the compounds of the future and understand them.
What would you say then to kind of sum all this up? What advice would you give to someone who's following this? They're obviously fascinated by this. It's still very big on social media. Lots of people following it. What advice would you give them as this kind of story unfolds going into the next sort of couple of weeks? Yeah,
well, I suppose the important thing is to sort of educate yourself about what should a superconductor look like? Yeah. For example, in this case, what tests should be done for a superconductor. And these are sort of available in all good textbooks, if you want. And then I suppose ask yourself, be critical, I think, of the literature in general, not just anything that appears on arXiv, but in a way anything that, to some extent, anything that appears in a journal. Ask yourself, is this actually what's claimed? Does it stand up to scrutiny? What other tests could the authors have done? So in group meetings, for example, people in my group will every so often make a literature presentation of somebody else's work, and comment on it, and sometimes the comments are, well, they should have done this as well. Or,
some tough love.
Well, actually, yeah,
they're quite savage.
Can be quite tough. Yeah. So, so I think do be cautious and sort of question what you've seen, question what you've measured. Is what you see in your sample due to some impurity, for example, and that's a case here, is that the sample's certainly not pure. So, and the solid state chemist is sort of constantly trying to eliminate impurities and make a single phase where you know what you've made. So that sort of persistence is important. Making reproducible samples is important. So that also hasn't really happened in this case. It should be, sort of, if it's real, you would expect rapid reproduction across several research groups.
That brings me to one final thing I wanted to ask that just kind of isn't on the questions, but kind of just following up a thread on what you said. You talked about the last kind of, I think you said it was around 2008 where there was this jump in the arsenide superconductors. How does the kind of furore at the moment compare with that, and compare and contrast? One that definitely sort of took off and was an actual thing, and there was a superconductor here. How does that compare and contrast with what we're kind of seeing at the moment? And can that give us any, vague probability estimate of what's kind of going on here?
Yeah, I mean, the iron arsenide story is quite an interesting one, because the effect was originally discovered in a lanthanum iron oxyphosphide. And the superconducting transition temperature was relatively low, so it was about 4 Kelvin or something, and that was published. And there was quite a lot of such a TC of 4 Kelvin is not particularly remarkable. A lot of metals become superconducting at that temperature, and there was quite a lot of skepticism from experts that this was a new class of superconductor, partly because iron compounds you would expect to be in various ways strongly paramagnetic or ferromagnetic. So I do remember some people were quite skeptical that this was a real, that it was really the sample that was claimed that was the superconductor rather than some impurity. But then the same group then published on the arsenide analog. And the superconducting transition temperature was about 25 Kelvin, so much higher. Not many things superconduct at that temperature, and so it must have been new. And I think that's really what lit the spark.
But the follow-up was quite rapid, and
follow-up was very rapid. So then there were lots of groups working on that, and sort of almost every day there'd be a new material, new measurements or corroborating measurements, showing these.
There weren't just grainy videos of specks of things floating.
That's right. No, there was the full analysis. Different qualities, but generally speaking, they were all these measurements were showing the Meissner effect or zero resistance or the heat capacity transition, and they were reproducible. Sometimes it took a little while to work out exactly what the composition was. But that's sort of fair enough. It was.
But if this is to be something that holds up, something that is a room temperature and pressure superconductor, we would expect to be seeing over the next couple of weeks, over the next month or so, more papers coming out showing the same thing, showing these changes in resistivity, showing these changes in heat capacity, showing the Josephson effect, showing the Meissner effect, these kind of things. We would expect to be seeing a kind of repeated drumbeat from different groups of.
Exactly. We should if it's really a high temperature superconductor, you would expect to see numerous replications which all agree, and they would show the measurements that you described, show it going through the transition and so on. So at the moment we're a long way from that. All we've got is this well, some indications of low resistivity, although the data don't look terribly good, and this rather, what I described as rather lethargic. Now, given the size of that magnet, I would expect that to ping
propelled up to the ceiling.
Absolutely, yeah. So there's something interesting to explain. It's generated quite a lot of interest, but I think we're a long way from really a new set of materials, I think.
Professor Clarke, I think that's a very good place to leave it. Thank you very much for taking the time, particularly on a Friday evening. I know you've got some holiday coming up now, so you can look forward to that now.
Indeed, yeah.
Is there anywhere where you'd like to point people so that they can keep up with the work that you're doing, or keep up with more work on this topic that would be useful to them?
Yeah, I mean, I think we're not working on this itself, but my group works at the Department of Chemistry at the University of Oxford, and we make a range of solid state compounds and look at their properties, tune their compositions to change their magnetic and electronic properties in their structures. And there are lots of groups around the world doing that. We collaborate with solid state physicists in the University of Oxford, Stephen Blundell, Andrew Boothroyd, and so on. So we're sort of part of an ecosystem that tries to make new compounds and understand their properties.
I will make sure that your group website and the links to the work are down below. Is there anywhere else you'd like to or suggest people look to kind of keep up with this idea? I guess the idea would be to keep kind of looking at the archive and see.
I think the archive is the place where things will appear that are reliable. So I would look there. I mean, I've sort of I've sort of kept an eye on this topic, and I think a quick look at the archive in the morning is the way I deal with it. You can get pulled into the Twitter sphere, whatever it calls itself now, and that
X sphere or so. It just sounds all right. Yeah,
a bit curious. But I think, so I would caution against people spending too much time on it, actually. I mean, I should obviously watch this video.
But, but keep an eye out for what the experts are saying and the replications coming through, rather than worrying about there's a rock floating a little bit above a magnet. And
definitely don't worry. Don't panic is also important.
Yeah.
And wear safety spectacles. And there's a small bear in the background. He's wearing safety spectacles.
So be like our friend the bear in the background.
Be like the bear. Yeah.
Professor Clarke, thank you so much again. I really, really appreciate it. I'll make sure all of those links are down below. And have a lovely holiday. And let's stay in contact on this. And hopefully we can talk again soon.
We'll see where it ends up. Thank you very much.
Exactly. My pleasure. Have a lovely holiday.
Thanks very much. Bye.
Thank you. Bye now. Bye. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.